Poczekaj.
O, już idzie.
Dobra, idzie. Okay, so this is a short history of the null scri. Here, as you see, I mentioned Trautmann 58 because it was really a first paper, in my understanding, which properly described outgoing radiation condition. The success of this paper was that the total energy diminished or at least didn't increase in time. But the paper was then forgotten, I must say. And continuation was, there was no continuation. The approach of Bondi and then Vandenberg, Metzner, Sachs was completely different and much more known. It was based on foliation of space-time by null surfaces of the same nature as in Minkowski space, null cones in Minkowski space. Then some expansions in inverse distance was taken. Coefficients were defined as so-called Bondi mass, Bondi angular momentum, perhaps, and integrals of these aspects were total energy, for instance. And again, the total energy was diminishing, and the rate of change was defined by so-called News function. So Sachs generalized this to from axisymmetric approach of Bondi, Vandenberg, and Metzner to general case, and soon later Penrose proposed approach with conformal compactification. In this approach, as you know well, the intuitive notion of null infinity from the previous work was mathematically well defined. So if you are interested in history of this first approaches to radiation, you can look about Trautmann. As you see, I don't send you to Trautmann work because it is rather difficult to understand and to translate it into modern language. But if you read Hrushchan, you will understand what was in the paper. About Bondi-Sachs, I thought that, of course, you can look into original papers, but also quite recently there is a long paper by Medler and Winnicur, Scholarpedia, something which I don't know well, but it exists. About Penrose compactification, you can just look around, take any book, and you know this. Everybody
maybe
knows.
Can I just mention that this paper by Medler and Winnicur is using a much better notation than the original papers. So it's it is much better to read and to understand.
So this is why I mentioned here, because if you want to understand in say finite time, it is better to look into this paper. But thank you. What is Bondi-Sachs metric? You know, first of all, you can imagine you can write the Schwarzschild metric in Eddington-Filkenstein coordinates, and it is the simplest example of this Bondi-Sachs approach. U is kind of a retarded time, and R is a distance along null arrays, which tend to null infinity. Intuitively, we understand what is this, but also we can pass to the Penrose approach if we take conformal factor 1 over R, and then we can introduce new coordinate omega, and the null infinity scri plus is exactly at omega equal to 0. The conformal metric is well-defined metric up to boundary. On the boundary, as you let me see if I can use Yeah, I can use this. At boundary, this term vanishes, but this term, it depends. Yeah, in point of boundary, this is well-defined Lorentzian metric. Yeah, the metric induced on boundary is just this one, because we put omega here under derivative. So it means the boundary is null with spherical metric, and the structure of the boundary is just a real line, means U times two-dimensional sphere with standard metric. And what they assumed simply is a generalization of this metric. But of course, we have much more functions. Here, everything is defined already, and here we have coefficients, components of the metric. But this metric, as you see, there is a limited number of components. Yeah, we already use this property that U equal constant is a null surface. So altogether we have two components here together is 4, 3 components here is 7 instead of 10. So still there is one, so gauge is almost completely chosen. Still there is one gauge condition which we can impose, and original Bondi-Sachs work, they assume luminosity condition. It means that simply R is the same property as in the Schwarzschild metric, that the determinant of this metric on the sphere is proportional to the R to the 4th. Yeah? And in this case, the area of the sphere with this metric JB is as usual PR squared. Symptotic flatness means, of course, that this metric tends to this form, to the Schwarzschild form, perhaps without this, but if the next term in the Minkowski metric is just this one, and the total energy in the Bondi-Sachs approach is defined as the integral of this coefficient which appear in this expansion of this metric at infinity. And in this case, this Bondi mass aspect M depends on U and spherical coordinates. Yeah, so after taking integral over spherical coordinates, it depends on just on U, and derivative of total energy with respect to U is never positive. So the same result as first obtained by Trautmann, but it's a pity that these people in Bondi and Sachs, there's no reference to Trautmann. So it means that and Trautmann in '58 was giving lectures in London, yeah, and these people were there, but I don't know, they didn't understand what Trautmann says or what. Perhaps Piotr Hrushel knows. I don't know what is the reason why this until now in Medler and Winnicott there is no reference to Trautmann again. I don't know the reason for this.
I don't know.
Okay.
But some people start using Trautmann Bondi mass and Trautmann Bondi mass loss.
Of course, you,
terminology.
Kijowski, you really did some effort to propagate this.
Yes, so especially the Yao school, which is of course very influential. So it's going to grow.
Okay. After 60 years, yeah, it's going to grow. No, much earlier, of course. Yeah, thank you. Now, the conformal approach means that we assume that conformal metric exists. There is a boundary. Here, this is a minimal approach. It means I assume only that boundary is scri plus without scri minus, no I plus, I not, and so on. Only future null infinity is present, like in the Bondi-Sachs approach, combined with Penrose, of course. And now, what we can do if we start from the scri? We can, first of all, we can choose coordinates on the scri. Yeah? And U coordinate must be such that U constant is just a two-dimensional sphere. Yeah? If I assume this foliation, also I can adapt coordinate U to be constant in leaves of this foliation. du is orthogonal to the foliation. It is natural because then you don't have cross terms in the metric, if they would be some. Yeah? Now we can extend this foliation to the neighborhood of the scri. We simply, this is usual standard procedure, we send past null geodesics orthogonal to sections U equal constant. Yeah? You can imagine, I don't have picture, but pictures can be found quite easily. So in this way, you get kind of null cones which cross scri plus along two-dimensional spherical surfaces, part of a null cone. Now, the other coordinates like U and XA are transported from the scri plus along geodesics, null geodesics tangent to this surface is U equal constant. So altogether, you get some system of coordinates which is adapted to the scri and to the null surfaces. Finally, we can choose the fourth coordinate to be the affine parameter of this null geodesics going to inside of space-time. I prefer affine than luminosity, so this is why, of course, this is equivalent, but okay, so affine gauge, why do I prefer affine gauge? Because this affine parameter is a well-defined geometrical object for geodesics, and luminosity condition doesn't have a place in mathematical approach. And the second reason is very practical, that simply the inverse metric is much easier to calculate and to remember even in calculations because there is no denominators in these formulas for the inverse metric.
Jacek, why do you put minus at the omega term and not plus?
Because for dr is plus, for 1 over r derivative has minus. Yeah. You divide metric by r squared, and if you pass to d omega, you get minus.
Yes, but I've forgotten about my r. Now I have only omega, so I don't care, but okay.
So if you have plus, you are on scri minus, simply.
Well, let me just comment here that, can you go back one slide, Jacek?
Mm-hmm.
Yeah, so this idea to using the affine gauge, so I think why not, of course, but let me just really say that I spent quite a lot of time working on the characteristic constraints. So that's the equations which follow, some of the equations follow here. Mm-hmm. And this luminosity parameter is, without it, you just, it's very hard to understand the structure. So there are, so it has really magical properties. So I think we tried to use this affine gauge and we just couldn't get much out of this. So I'm not saying one shouldn't, and I think it's probably a very good idea to check other gauges, but certainly the luminosity gauge has magical properties.
Yes, I agree. It has magical properties. One of the useful properties that the energy is easier to define. Yeah? This is just integral of this coefficient mass aspect, and here for the affine, in affine gauge is something different. Yeah, we have to correct it. Yeah, I agree that for some purposes luminosity gauge is better. Now equations, yeah. Okay. Equations for this, if we start from the scri and we want to write Einstein equations in neighborhood of the scri, it means vanishing of the Ricci tensor of the physical metric, tilde metric, but we want to write them in terms of the conformal metric. So we have to use this transformation formulas between Ricci tensor of the this is physical metric, and this is Ricci tensor of the conformal, non-physical metric. Yeah? This is the left-hand side, it means this one. So we correct the Ricci tensor of the conformal metric by this tensor, which is defined by second covariant derivatives of the conformal factor. And as you see here, there are some singularities, like 1 over omega here, and even second order singularity in this term. So if, in fact, it is a source of difficulties, yeah, to define initial value problem with scri as a part of initial manifold, yeah. But you also know that Helmut Friedrich was able to overpass this difficulty 40 years ago, and there are statements about solutions of initial value problem with characteristic data, including scri. Yeah. So if you assume that there is no second order pole, yeah, so it is clear that this must be proportional to omega at least. Yeah. So this means this. Yeah, but this is proportional order. This is O, order of omega. It means that G naught GUU in other language is also proportional to omega. So this is simple part. Now you assume that other components of this tensor are regular. So no single pole in these components mean that UA components are proportional to omega squared. And last condition that this spherical part of this tensor is regular means that derivative hat means value on the scri. Okay, so this is tensor conformal metric on the scri. Derivative with respect to u is proportional to this metric. This means that the boundary metric is proportional to the standard spherical metric. This is so-called uniformization theorem, but we know this. Proof is not easy, but result is easy. And because of this proportionality, we can use some coordinate freedom. We can change coordinate omega, so the conformal factor, and also the retarded time u, and we can eliminate alpha. Yeah? Alpha becomes 0, and the boundary metric becomes simply spherical metric. So there is there is agreement between this conformal approach and the Bondi-Sachs approach. Yes, we get on boundary, we get spherical, standard spherical metric. Yeah? So we can, at this stage, we simply know that we have such expansions of coefficients of the metric. So this is because of this regularity properties, the same with this. And here is the boundary value of the spherical part. Now, the full set of Einstein equations is not necessary to consider. We can take part of this set and different. In fact, Bondi-Sachs takes slightly different set of equations than I prefer, but the difference is cosmetic. I take this because I don't want to calculate traces of the Ricci tensor, yeah, because I will do some expansions, then having a trace is additional difficulty, but still you can prove that all Einstein equations are equivalent to equations. As you see, this is easy to remember. No index 0, no index u in the equations. Only other equations are included, but there are two equations, sorry, which we have to include, namely second order part. This 2 in bracket means this is part proportional to omega square. So there are two equations on boundary, yeah? Which cannot be obtained by Bianchi identity from other equations.
Jacku, index 1 corresponds to omega. Can you remind?
Index 1 corresponds to omega. Okay. Index 0 corresponds to u.
Okay.
Now the simplest equation is this one, and this can be written in very compact form, and see what we get. I didn't explain. I will not write equations in finite form. I will simply find what we can get from equations. Yeah, which coefficients can be derived from which equation, and so on. So I take expansion in omega. It means I assume smoothness of solutions. I expand metric into the Taylor series. Perhaps it's not convergent, but still I can do it. And to find relations for coefficients in the expansion. So this is very easy equation, and this equation can be Jesus, I will not use the cursor because then I change screen. In this, from this equation, we simply obtain trace of, in bracket k plus 2 means this is proportional to the omega to the power k plus 2. Yeah? G hat is just the spherical metric. Look into this as the spherical metric. It has minus sign. This is why I don't write minus SAB. I prefer hat because I want to avoid problems with signs, yeah? That I don't remember what's what. But you can consider G hat AB as spherical metric. So you see that the trace of this tensor GAB with respect to the spherical metric is given by lower order coefficients in the metric. And in this sense, I want to read all equations. Yeah? The next set of equations where you have omega A subscripts, the lowest order says that the QA is the first coefficient in the component UA. So this is the component which contains possibly the angular momentum aspect. Yeah? Cross term du dxa. D means du times derivative of the spherical coordinate. So it simply says that this is divergence of the first correction to the spherical metric. NAB is almost New's function in the Bondi approach, almost because the New's function corresponds to time derivative of the tensor NAB. NAB itself is so-called asymptotic shear tensor of null geodesics along this null surface is u equal constant. Yeah? So there are interpretation of this, of all these low order coefficients. Okay, so for all other coefficients, as you see, they are defined by lower order. You know? By lower order, because on the left-hand side we have k plus 2, on the right-hand side we have k plus 1 at most. Yeah? So in algebraic way, we get all other coefficients, with some exception that for k equal 1, we cannot get it, because on the left-hand side there would be a factor equal to 0. So what do we get for k equal 1? For k equal 1, we get divergence of PAB. What is PAB? Is next term in the spherical part of the metric. Yeah? First term is standard spherical metric. Second is NAB. Third one is PAB. Yeah? So next correction to the spherical metric. And you get equation for this. Yeah? So this is third coefficient. This is square of second coefficient in this metric. So formally you solve it, and you find that it is given up to a TT tensor. It means traceless and divergent less tensor on the sphere. But there is no such tensor. There is no regular solutions of this equation, you know, only singular solutions. So if we assume smoothness, we have to take 0. In luminosity gauge, it is a similar expression, but perhaps the coefficient here is different, but it's also proportional to the spherical metric. This is, in fact, minus spherical metric. Okay, let me say. So this is the most difficult part.
Jacek, may I have a comment?
Yeah.
When you have a TT tensor on a sphere and this covector, which is a divergence of a TT tensor, so if you remove dipole part of covectors, this is isomorphism on a sphere. So it is much more than when it vanishes, then there are no TT tensors. If it is something, then also there is a unique TT tensor. So not only, how to say it, you
want to write non-homogeneous equation?
Yeah, non-homogeneous equation has also solutions, and up to dipole part they are unique.
Okay, so in fact I will use this what you said in next part of the talk. Yeah, these equations are the most difficult part. Yeah, but still the first two equations are easy. Simply equation. Zero order equation, it means the value on boundary, if you assume that this is 0, this is already non-singular, yeah? It is assured. But if we assume that the value on the boundary is 0, then we simply get that the coefficient B, what is B, is the first number, non-trivial number in G not component, GUU component. So if it is asymptotically Minkowskian, it must be 1. And due to this equation, it is exactly 1. So G is asymptotically Minkowskian. Yeah? The next equation is trivial because it contains U derivative of equations which already were satisfied. Now, what about higher order equations? If we take trace of the higher order equation, but I said that I don't like trace and I calculate trace here. Yes, but I take trace with respect to spherical metric. Yeah? So it's not the same as the full metric. So this is easy to take. The other one without hat is difficult. So I take this trace with respect to spherical metric, and what do you get? You get next coefficients in front of GU squared. Yeah? So first one is 1, then minus 2 masses over R. The next one will be given by this formula and higher k. So this right-hand side simply means an expression which depends on these components, lower order components. In fact, I would, for this seminar, I could use maybe some easier notation than writing all these coefficients. Now, what about the traceless part? Traceless part gives us time derivatives of trace-free part of this tensor, of this metric GAB on sphere. Yeah? So we get all time derivatives of components for k higher equal to 2, we get time derivatives. So if we have time derivatives defined, it means the only freedom is initial value at some fixed u. And this is known from Bondi and Sachs that this is really free data for solutions. The last two equations, which from this set of Einstein equations, simply say what is time derivative of the mass aspect and angular momentum aspect. And again, the right-hand side is simply function of this shear tensor NAB. And in the second equation, first, if you have already mass, you can calculate angular momentum aspects up to initial value at fixed u. So this is well defined. And so all this can be summarized in the following way, that we have, say, formula for physical metric, because it is, say, finally we are more interested in physical metric, not in the conformal one. So we have expansion of coefficients, everything as expected. This is 1, so the metric is asymptotically Minkowskian. Second term looks like in the Schwarzschild, but this function m now depends on u and depends on spherical coordinates. Yeah, the integral of m is, say, almost energy, but because it is affine gauge, it's not exactly energy. We have to use some different formula. Now, this is the part with this angular momentum aspect. As you see, this is not the first coefficient in this component, is the second. The first one is already defined by NAB, the shear tensor, which is free. This is free. It defines this part, it's enough. Yeah? If we have NAB, we know this, we know this. So there is no room for free angular momentum. Angular momentum appear here. What else? Yeah, so your initial data, everything perfect as in Bondi-Sachs. So this is just to remember how the Einstein equations can be solved if we have expansion in inverse powers of the distance. And Bondi mass aspects, if we pass from the affine gauge to luminosity gauge, we get difference, which is square of the shear tensor differentiated with respect to the time.
Jacku, and in your assumptions, this NAB is traceless?
Yeah. Perhaps I didn't write it. This is free to choose. Yeah, it is better to choose trace equal to 0. It looks easier. Yeah. Yes, it's traceless. But this is choice of distance r, which is
right.
Okay.
So I'd like to make a comment on this method of solving Einstein equations, because of course you can just think of this as providing you some kind of propagation equations, but it's viewed in this form, it doesn't look like this has any good mathematical properties which one could exploit to really prove something. So there is a recent paper by Hilditch and friends which claim that this can be put in a hyperbolic form. So I haven't checked the paper, and I'm not sure how correct it is. But apparently, this scheme can be put in a form which can be used to prove things rather than just giving a plausibility argument.
Yes, but you mean that? Yeah. In fact, I was also interested in this, but I don't know enough about differential equations. So you say that the scri can be initial surface, and evolution from the scri would be hyperbolic?
No, from Bondi coordinates, right? So you have this null hypersurface, which gives you the initial data, and of course, characteristic initial value problems are well known. So it's nothing exciting about this. But the interesting thing is that this particular gauge conditions and setup is actually compatible with some kind of well-posedness, which I'm not taking any responsibility for what Hilditch and friends say, but apparently there is a way of making it work.
Thank you very much. Let me add that Piotr did also wrote papers on characteristic problems and review papers too. So you can look into these papers and to read about other works. Yeah? So I recommend review papers of Piotr. Stationary. So finished general case. We pass to stationary metrics. I think it will be a little bit more interesting, stationary metrics. So let us assume that we have a metric which is stationary, but also admits the conformal compactification in this restricted sense that the future null infinity on. Yeah? And now we want to construct coordinates of Bondi-Sachs type to put metric in this especially simple form. Yeah. So again, this is kind of standard, but let me put it into some points. Yeah. So the first of all, I assume that the scri is a product of real line times two-dimensional sphere. It is not written, but it should be written. Okay, so first of all, from the scri, certainly we can send some at least small but null surface to the past, yeah? And this null surface sigma naught, we choose it in such a way that intersects scri along spherical surface. But we know that if we have stationary metric, we have Killing vector. If we have vector, we have a group of motion, yeah, which preserves metric. So we can construct other surfaces, null surfaces from sigma naught, simply by Lie transport along this Killing vector field, yeah, to say to the future. For instance, we shift it. Yeah? So we get locally, we get foliation by null surfaces. At the same time, we, from this sigma naught surface, on the sigma naught surface, we choose, say, affine distance, spherical coordinates on cross sections of the surface, and we propagate all these coordinates along this Killing vector field. Yeah? So we use this group of motion to transport coordinates. So the structure will be preserved by the Killing vector by construction. Yeah? Finally, we can, I'm not sure that we get the same R everywhere and will be always, because we don't assume only that this is a affine parameter. It is special affine parameter. It means that G01 component is equal to 1 exactly. Yeah? We have this freedom to choose, so we do it. Of course, I included the last point into this list because non-singularity of the Ricci tensor is easy to translate to conditions on the metric, and we really get the Bondi-Sachs form. But there is one problem here. Like in general case, the asymptotic value of G0 component does not have to be 1 without using Einstein equations. It's just something. And also the boundary value of the metric on the scri does not have to be standard metric, can be multiplied by a factor which is U independent. Now we cannot use the transformation of omega and U because from the previous, say, chapter, because then we introduce artificial dependence on time U, which we don't want. So we cannot do the same, we cannot apply the same method. But we can take Einstein equations and we get what we want. We get B equal 1 and we get alpha equal to 0. From which equations? This equation, it means the boundary value of the Ricci tensor, physical Ricci tensor, not component on the boundary, say simply with Laplacian of B is equal to 0. This Laplacian with respect to this metric, but it doesn't matter. Like for standard spherical metric, we get B equal constant. There is no other solutions, no other smooth solutions. Yeah. If we know that B is equal constant, then we can rescale U and R by constant factor and we get B equal 1. So this is not bad. If we know that B is equal to 1, we substitute it into equations, this one, and we get that Ricci scalar of this metric here is equal -2 because, again, I use minus sign here. But from this, we simply get that, that it must be standard spherical metric, no place for factor e to alpha. Ricci scalar decides about good property. So now we come back exactly to the same equations as before, but simply U derivative of anything are equal to 0 now. Yeah? So we adapt to previous equations, but okay, so some equations, okay, before we consider this long series of equations, let us consider these lower order equations because they put strong restrictions on coefficients. Yeah? For instance, this equation, it means, in fact, this is the first non-vanishing component of the Ricci tensor with indices time and spherical one. Yeah? You find that gradient of M is derivative of, what is this? Q is another part of the metric. Yeah? This is this component in G not A. In the metric with this indices, Q is the first component in this part of the metric. And here you have covariant derivative with what? With respect to what? To the spherical metric. You have anti-symmetric part of it, and you have divergence of this. So you get such equation. I say that this equation has rather trivial solutions. Simply, you take covariant derivative. This is Levi-Civita tensor in 2 dimensions. Yeah? And you get Laplacian of alpha equal to 0. What is alpha? Alpha is just the Q symmetric part of this derivative. Yeah? And again, because alpha, the only smooth solution is alpha equal to constant, but this alpha must be 0 because if I integrate alpha over the sphere, I integrate divergence. So I get 0, yeah? So alpha must be 0. If alpha is 0, it means that QA is just a gradient, yeah? If QA is a gradient, this is 0 and M is constant. So good. So we have some strong consequences for coefficients. Next equation, the omega order of this Einstein equations of the order of omega. Here you get what Jacek added a few minutes ago. We have divergence of traceless tensor equal to something. This something now is just a gradient of function Q. So I postulate, okay, since the right-hand side is not general, is of special kind, I also postulate that left-hand side has some special kind. And I postulate NAB in such a form. And yes, this equation can be satisfied, provided that function f satisfies this equation. Yeah? So as you see, this is for the angular momentum equal 1. Yeah? The harmonics up to spherical harmonics with L equal 1. But okay, so you see that the problem, we have always solutions for F, for any Q, except Q which contains first harmonic, spherical harmonics. Yeah. So if Q is a combination of first harmonics, I cannot invert this operator delta plus 2 because it simply kills this part. Yeah? But then you can simply check that. Okay, so let us assume that Q is a combination of these spherical harmonics. It turns out that there is no solutions. This equation has no solutions if Q is a combination of first harmonic sphericals. So it means there's no problem, F exists, F is given up to, again, it is up to, okay, now I can, F is given up to first harmonic again, but NAB is uniquely defined in this way. So I know, and why do I want a solution of this type? Because I can gauge away this type of tensor NAB. I can gauge away by means of the Bondi element of the Bondi-Sachs group, means super translation of special kind, exactly with this function f, and by shift of the radial coordinate. So it disappears. Yeah? So good for us. Simply NAB is equal to 0, and we have simpler expansions. Yeah? Simpler because we don't have middle term here. In fact, NAB is equal to 0. It was a term in front of R. Constant term was depending on NAB, so it's again 0. So there is a big gap between these two terms. Yeah? But also there is no first term in expansion of this metric component. The first term is just angular momentum aspect. Yeah? It is important that this still we have freedom of translations of U and R with this. And people who know Bondi-Sachs group, they know that this function plays a role of the translation subgroup in the Bondi-Sachs group. Yeah? I will not spend time on this because everybody can calculate how translation in Minkowski space change cones, simple cones in the Minkowski space. It is really translation, corresponds to translation. Okay, what else? The next low order equation, which is interesting, is this one. So spherical part proportional to omega square. It says that symmetric part of the covariant derivative is proportional to the spherical metric. But this means exactly that this field is conformal Killing field on the sphere. And we know solutions of the conformal Killing equation on the sphere. These are rotations, and these are really conformal transformations. In other language, we know that the conformal group of two-dimensional sphere is also isomorphic to the Lorentz group. So these are rotations in the Lorentz group, and these are boosts in the Lorentz group. Funny. What is funny? Because you see, this part is translation. Yeah? B times R has the same. This is exactly this part, because first harmonics are X, Y, Z components of the vector on the sphere. Yeah? So on one hand, this is translation in the BMS group, but on the other hand, these are Lorentz transformation in the same group, I would say, because Lorentz group is present in BMS. Perhaps for me, it was something strange. Perhaps somebody can explain me how translations can be Lorentz transformations. Boosts, I don't mean, but who knows? So what are residual transformations? Residual transformations in the BMS group are these transformations. We can use these transformations to remove this part if mass coefficient is different from 0. Because we simply find what is transformation of this coefficient under these translations. We find that transformation is very simple of this type. If m is equal different from 0, we can simply remove this part by choice of f. This part remains, but of course we have still freedom of rotations in three-dimensional space. So we can put this direction along axis z, and we get exactly what is for the Kerr solution. Yeah? This is expression for the Kerr solution if we direct the vector A along axis z. What is for n equals 0 is more complicated, and perhaps
so the mass aspect is constant now,
yes,
or is
yes,
it still
yes,
a function? It's constant. Mm-hmm.
So the first term in this expansion is in fact the same as in the Kerr metric. Now we can consider now the long series of these equations with higher orders, and we get simply these coefficients in some recursive way, but in algebraic way. Yeah? So these are not, this is not a problem. The only problem is that in these equations, there was time derivative of the metric, and it vanishes. So we have to look further into structure of these equations. And if we write these equations in more detail, we get this type of equations. Yeah? Maybe you don't remember what is what, but this is the spherical metric. This is this U A metric, so mixture of time, space components. But this part is defined using one of these algebraic equations, this part. So I can substitute from this algebraic equation an expression for this part. And you see, I get the same order here as here. If we write this equation after this substitution, we get an equation of this type. So spherical Laplacian plus some value action of tensor GB at order K is given by lower order. But in fact, this looks nicer, but for computation, this is better. But it doesn't matter. It is my first expectation, but I was, in fact, I did a mistake. And for a few days, I thought that there is a unique solution of this. And I was completely lost, you know, because in this case, the Kerr solution would be the only solution. Fortunately, it is not. It means there is a room for Tomimatsu Sato, double Kerr, and other solutions. I didn't exclude them. Yeah. Okay. To say something about this equation, let me prove such a simple lemma. You take a traceless tensor. It's capital N, but is of course there's motivated by this small a, small n tensor, that it can be decomposed. In fact, this expression was obtained for this small n tensor and then removed using the coordinate transformation. The new part is this one. But in fact, this part is obtained from this part. So you will see. So proof.
So what is eta and h in this lemma?
Eta is Levitivita, h is any function. F and h are free functions.
I see. So it means there exist functions.
Yeah. Okay, I didn't write. F and h are free functions. Take divergence of the tensor, general tensor. The right-hand side is some vector, covariant vector here. But we can decompose it into gradient and dual of gradient. Yeah? On two-dimensional sphere, there is no harmonic functions other than constant. So we have this simple decomposition. Now, this is a part which we already solved. Yeah? If we take this, it is equivalent to this. So solution is like it was before, and a relation between function on this side to function on this side is via this Laplacian plus 2. For this part, we simply multiply this equation by Levi-Civita and we get dual equation. Yeah? Dual equation, here we get a dual tensor, but it's again symmetric and traceless. So we use the previous result, we decompose it in such a way where h is some function, again, related to capital H in this way. And now I calculate back I take the second dual. Yeah? So I take dual of dual and I get such solution for original tensor. So this is end of proof. Now, what can I do with this? So I take these components of the spherical part of the metric tensor and I decompose them in this way. I use these two potentials F and H. of course, I have second derivatives of these potentials. So it's not terribly easy, but still we can do this. If I calculate the divergence of this, I simply is the same expression, but with other functions. Yeah? And finally, I write equations, these equations which were lost, yeah, for some time. And it turns out that we get equations of this type, with Laplacian plus k minus 1 acting on potential is given by lower order terms. But this right-hand side is not easy to calculate. It means I have some lower order term. I have to calculate the potential F and H for this right-hand side. So this is not completely simple, but you see, it is consequence of this is clear. Yeah? But assume that solution exists. F and H exist. If it exists, it's given up to solution of the homogeneous equation. Homogeneous equation is satisfied by spherical harmonics with index k minus 1. So solutions are defined up to combination of spherical harmonics. Okay, but what happens if the right-hand side contains this harmonic? This is a problem. This could be a problem. I didn't verify this completely. I hope that this problem does not appear, that we never have on the right-hand side these harmonics, but who knows? If we have harmonics on the right-hand side, it means we get some restrictions, yeah? Because if we have these harmonics, there is no solution, and so on. So possibly there are some restrictions on the lower order terms if we have to find higher order terms. Yeah? But this is to be done. So this is my last slide with conclusion. So every stationary metric, as you see, can be written in such a way, and you recognize here the Schwarzschild mass. Here you have angular momentum of the Kerr metric. Here you have spherical metric. There is no terms of order R or constant. Here is a kind of quadruple terms, but what does it mean, quadruple terms in this setting? It means these are the second derivatives of harmonics, of second harmonics. Yeah? So it is not by Hansen or Newman, I don't know, these are called tensor harmonics, things like this. So these are tensor harmonics. And how many parameters? I wrote how many parameters, because this is counting how many components of this we have, and also twice, because F and H, there were two possibilities. So there are twice many parameters available. So at each level, in the next order, we can get still more parameters. Next one order, again, some maximal set of parameters can be obtained. Of course, if we have here some tensor, then next order here and next order here will contain parameters from this part, yeah? Because there are algebraic equations which still will contain these numbers here. So it becomes complicated. Now, if you assume axially symmetric case, then this is the example, what is this Q part? So QAB times derivatives is something like this. So what we can do else? I would like to know how to place into this picture other solutions, axially symmetric solutions, but I started with Tomimatsu Sato. This is hard job. The same with double Kerr matrix. Another problem which bothers me is analyticity. Perhaps Piotr knows and can comment on this. In space like infinity, if metric is stationary, it's analytic. Yeah. What about null infinity? Perhaps it's the same. So if it is smooth, it's analytic. I don't know. If it is analytic, then I can make a relation to the space-like infinity. Yeah? Perhaps I can relate these moments like Q and other moments to moments of Garrosh and Hansen and so on. So I don't know simply. And if somebody knows about these relations, just let me know, because another problem is cosmological constant. Here I have some results, maybe are not, but I couldn't, I was not able to contain them into this picture. So thank you very much. That's all.
So thank you very much for the talk. So now we are the time for questions.
So maybe let me just not ask a question, but answer what you said about analyticity. So of course, a metric, so a vacuum metric is analytic in suitable coordinates in space-time. But here the question is, does the analyticity propagate all the way to scri? And this is not an obvious question.
Mm-hmm.
And I wrote a paper with Bobby Bike about this. But there's something funny with the dimensions. So I think we can just do it in even or odd space-time dimensions. I don't remember now which, and this has to do with proving relevant theorems. So in 3+1 dimension, I just don't remember whether it works. Let me check.
Okay, thank you very much.
Jacek, have you assumed anything about the Weil tensor in infinity? Anything additional to the Einstein equations?
No. The properties of Weil can be somehow read of these equations, so some of them will vanish. Yeah, but no, there's no extra assumptions.
Right. And now, so what can you read about the Weil tensor in the case of this stationary case? So is it, for instance, of the Petrov type D a little more than generic?
I don't know, but type D, no, I don't. You think so? It would be too much for me.
Well, I mean, asymptotically.
Yeah. You know, my problem is with computations. Namely, I am not fluent enough in using Mathematica, for instance. And there are so many errors in computing components of the Ricci and so on, correcting. So, first, I should learn how to use Mathematica, and then I could combine calculations by hand and say, looking into correlations of different expressions and to check what is done by symbolic program. Without this, I don't see continuation. It is difficult. So I'm not sure that I would like to compute Weil coordinates by hand, but maybe it's not so bad. Yeah, maybe not.
May I have a question or remark?
Yeah.
Basically, it's not a question to Jacek only. Piotr made a comment about the verboseness of the equations. I think David Hilditch and collaborators tried to use it in the hyperboloidal initial value formulation and not in the null characteristic one. And my first PhD student, János Kerr, was probably the first using Helmut's formalism when he proved the existence and uniqueness of solutions to the asymptotic characteristic problem, where you have a null hypersurface, cutting scri and going into the space-time, and he used part of the scri to set up the initial data there. So it is not easy to see how Jacek's formalism could be immediately put into some sort of well-posed setup, but it's really interesting. I like this talk. Thanks, Jacek.
Thank you very much. I'm happy that you mentioned Kerr, because I saw this paper 2012, perhaps, something like this. And yes, is it, I'm a little bit lost when I look into these many papers of Helmut Friedrich, what was done, what wasn't done, and what Kerr did. Friedrich, I think that Friedrich didn't consider exactly the scri as one of characteristic surfaces.
No, it was János, I think.
Yes, I think János was the first one who really treated this seriously, but this is one of characteristic surfaces. For Friedrich, he took simply some surfaces, but not on the scri.
Yes. I mean, he did this.
Do you agree, or because you also did work?
Yes, of course. So János had probably the first paper about this. Yeah. So there's various ways of doing this now, but István, well, the paper I had in mind is a paper by Hilditch and colleagues in October last year. So
actually, I haven't looked at it, so I don't know.
So they're really talking about the Bondi coordinates there. But so yeah, as I said, I haven't checked this paper. So
I mean, it would be strange to have a well-posedness result without referring them to part of scri. I mean, you need something in addition to the other null hypersurface.
Yeah,
of course, it's a mixed Cauchy problem. Yeah.
You need news functions, for instance.
Yeah.
So my ask to you is if you can help me in understanding these different relations, for instance, like relation to space like infinity for stationary metrics, at least, because for time-dependent metrics, probably there is no relation. I don't know, but for stationary metrics, I would expect it is related. Under what assumptions? So Piotr, think and tell me.
Well, I think that there's a paper by Beig and Schmidt who show that if you have a metric which is stationary and your I naught, it has a smooth scri. So then you can probably just use this machinery to put things together.
What about opposite?
I think also Helmut did something, he was always struggling with the problem how to relate quantities on scri to his cylindrical space infinity picture, and he did something definitely many years ago, 6 years ago for static, and as far as I remember, he also did something later for stationary. So it's worth to look up, what he did.
So I have to correct what I said. It's not Beig and Schmidt, it's Damour and Schmidt. So Thibaut Damour and Ben Schmidt.
Yeah, so maybe I will finish recording and we can speak later. So thank you again.
Thank you very much.